Hey. Okay, so this video is going to be on the production of amino guanidine via nitroguanidine to guanidine nitrate to nitroguanidine to amino guanidine, and in it will be several reasons as to why I think this method is superior over cyanamide hydrazine, and also what is the main fucking issue with it. Okay, let's get it started. Okay, so this is going to be very difficult to see, but this is concentrated sulfuric acid. See those white particles that are everywhere? That's guanidine nitrate. This is nitroguanidine synthesis. The mercury thermometer is 10 degrees. It should be between 10 and 5, but since it's not fully submerged, I think it's a little bit under, I think it's colder than it says it is. So yeah, this is, yeah, every time you do a little addition, it's not a huge increase in temperature, maybe 3 or 4 degrees, of course, depending on how much you add. You can see the temperature goes up a little bit. So this is step 2 in the overall process. Okay, so there's 85 milliliters of sulfuric acid, 96 or 7%, and 50 grams of guanidine nitrate. And this is step 2 in tetrazole, the alternative path. Guanidine nitrate's $6 at line, so figured give it a shot. This is not my sulfuric acid, but my boss does not need to know that. This should work out well. Okay. So what am I actually doing right there? And I think I can describe that pretty well. So first, let's just know what the molecule is. So this is guanidine, and when you make guanidine nitrate, it's the 3 minus, and that's the plus. So that's the salt. That is right there. Quite a bit of nitrogens, and I'm dehydrating that. I'm connecting these two groups together and spitting out a water molecule. So H2O, and then this is in the H2SO4 concentrated. And we're making that. So we get the salt and we remove a water molecule and it makes that. But I think the intermediate, I might be wrong, but I'm pretty sure the intermediate is something along the lines of, because as far as I'm aware, it's the nitrogen attacking it. So the nitrate structure sort of looks like this. Apparently some of that's sort of cool. So that's the intermediate looking. So even though this is a negative charge and that's a positive charge, in order to get the nitrogen to attach to nitrogen, this positive charge has got to go into there. So what I think occurs is this concentrated sulfuric acid will protonate this group, the nitrate group, into something like, well, N plus O minus, and then like nitric acid, or even further, so now we can make nitric acid into this sort of thing, and that will sort of the charge in this bond will go to that molecule, and we'll end up with some sort of and this charge will go into there. We'll end up with this nitronium group, but that still has a positive charge on the nitrogen, and this nitrogen has a positive charge. So the only thing I can think of is if somehow some intermediate, well, I mean, that nitrogen is still basic, you know. So it could be this group attacks the basic nitrogen in guanidine, 3+, and then this goes there and forms a bond, makes a nitro group, and we end up with the water molecule formed here, and this, you know, salts probably just I don't know, I doubt it'll be a salt. It'll probably just deprotonate into our final product. I think that's what occurs.
Okay, let's see if this will work. So, this is for the video. This is our product. It's recrystallized nitroguanidine. I think I got about 35 grams, which is like a, I don't know, like a 75% yield. It's fine in my opinion. This process works incredibly well. But we'll see what an issue is with this synthesis.
Okay. Okay, let's start. So this is a mix of zinc and amino guanidine. You can sort of see the amino guanidine crystals if it focuses. Focus, you fuck. Focus, you fuck. There you go. You can see the needle-like amino guanidine crystals, nitroguanidine crystals, surrounded by zinc powder. And you sort of, you know, you put that in to glacial acetic acid that you diluted, so I guess just regular acetic acid, and you continuously add in more of the zinc guanidine mixture and ice, and you make sure it's cooled to like you know, around you know, between 5 and 15. I think I'm gonna, yeah, and that follows this reaction. So last time wasn't so good drawing on the whiteboard, but I hope I can do better. So right now this is the compound. Okay, hand cam. So let's describe what I was doing earlier. This is a nitro group. And now let me describe its charge. So when you look at a bond, you have to consider that it's basically just a pair of electrons. Just a pair of electrons. A lot of electrons can just be by themselves as lone pairs. A lot of electrons can be part of a bond. But a bond is just a pair of electrons. And when two atoms share a bond, and they're the same atom, two nitrogens in this example, you basically split it. So each one of these gets one electron in this bond. But when two different atoms, a nitrogen and an oxygen, share a bond, the more electronegative atom gets it all. So in this case, it's the oxygen. And in this case, even though it's a double bond, it's the same rule. The more electronegative atom takes all. So that's where it is. If you calculate it, this oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8. So it's -2 because oxygen normally wants 6, but now it has 8. This oxygen's the same. 1, 2, 3, 4, 5, 6, 7, 8. -2. I'm not going to consider this nitrogen because it has more bonds, but just for the structure. This nitrogen, on the other hand, it has 1. It has 1 in this bond, and that's it. Normally, nitrogen wants 5. That's its normal state. Look at the periodic table. It has 5, but it only has 1 in this instance, so it's +4. -2 plus 4 is even. That's good. Now, for charge, it's a different thing. You have to consider it something else. When we're looking at why this has a positive charge, only one positive, even though it only has 1 electron and it wants to have 5, you'd think it would have 4 plus charge, but it doesn't. When you're looking at charge, electrons are shared. They're always shared. So this bond, they're shared. Split down the middle. But also on this bond, it's split down the middle. And these two bonds, it's split down the middle. So if you consider it, once again, this oxygen atom has 1, 2, 3, 4, 5, 6, 7. It wants 6, it has 7. So it has a 1 minus charge. 1, 2, 3, 4, 5, 6 has 6, 1, 6, it's neutral. We're not considering this nitrogen. This nitrogen, it has 1, 2, 3, 4. So it has 4, wants 5, it has a plus charge. Now I'm saying this because when I was doing this reaction, where an electron came in and was attracted to that, it's because A, electrons in this molecule have opposite charge, opposites attract, and B, this oxygen is so electronically deficient that it will go into this atom. So it will make this intermediate, but because it can't just exist on its own, this nitrogen just can't have an extra electron because it already technically has a full octet, technically. So then this bond goes into the oxygen. So you get this intermediate nitrogen radical, where the nitrogen has 2 electrons. One in this bond, 1 here, but so it has 4, now it has 3, but now this is a negative charge, which is fine because there's an H plus because the solution is acidic, and we get N radical OH O minus. That's how we continue on forward. Hey, guess what? The idea that this turns into that by making hydrogen is the intermediate is fucking wrong. I didn't know that at the time, but there's a better way of describing it. So this is the structure of the nitro group in the nitroguanidine. And if you look at it, this nitrogen is it has a positive charge. And in the presence of, let's say, a metal, what actually happens is that an electron comes, just an E minus, and it comes and gets absorbed into there. And this double bond of the oxygen gets sucked into there, forming N single negative, and a nitrogen radical. I believe it's 1, 2. Okay, so this is 2, 3. It's positively charged, massively positively charged. But I think this is a 2 plus charge at the moment, but it's an intermediate, so don't think about that for too long. Because what happens immediately is this oxygen attracts an H plus because of the acidic solution and turns into OH radical O minus. So this is now, because if you count the electrons, it has 1, 2. Yeah, it just got 2 electrons. So its formal charge is, well, I mean, no. I'm thinking of this wrong. This is not right. It has, because this one, it has 1 electron. These oxygens are taking up all the electronegativity in the bond, but this nitrogen, this bond is shared between it. So this one has 1 electron. Now it has 2 electrons, but its charge is, normally nitrogen is 5, but now it has 4. Now nitrogen has 4, so its charge is still plus. Okay, and here its charge is still plus. My bad, not 2 plus, just 1 plus. So a similar thing happens, right? Another electron comes into here, and we get a lone pair. Okay, so not a lot of writing room. Maybe chalkboard for the future, right? So electron went into the other thing. So now we got this group, OH, O minus. What occurs here is another sort of shifting of bond energies, where like the lone pairs on this oxygen attract another H plus, and we get something that looks like that. And what happens is this electrons get sucked up into that bond. So we get a water molecule leaving, and that's part of this dehydration. Or, no, that's just not the reaction, but water molecules leaving. So we are left with O minus. So this has still got a positive charge. But now instead of the 1 electron that we started with, now we got 3. Okay, so let's do this process again. Okay, let's erase the whole board. This is the intermediate. N O minus, positively charged. We're giving this another electron. Okay? So another electron comes in, goes into there. This thing forms their radical. O minus, H plus, because we're under acidic conditions, gets attracted to the O minus. We're left with H plus gets attracted to the O minus, and OH. Another electron comes in, and we're left with and OH. And if you actually count the electrons, this thing is negatively charged. So now another H plus comes in and puts itself on there. And now we got an H, OH, the fucking hydroxylamine. Well, you know what's going to happen? Another electron comes in. Forming an H single bond radical, and this OH, its electrons attract an H plus, and it forms this unstable H radical H2, and it sucks these electrons into there, forming another water molecule. So now we got N H radical, and another electron comes in. Now this process probably takes a fucking long time, which is why it didn't work in the video. But the electron comes in. Now we get N double bond. I mean, 2 lone pairs plus an H. And now it has a negative charge, which attracts an H plus. And now we get N H that, which is the group. It's the amino group.
Okay, is this working? It should be, okay. Fuck you, synthesis! Okay, that yellow looks orange. It looks like Gatorade yellow, like neon gasoline piss colored yellow. This yellow the camera sees is paler and less yellow than what I see. Fuck you, fucking synthesis. Fuck you, filtration. It wasn't filtering. I went through like a dozen filter papers, and then I was like, wait, why is the stuff that started yellow, but the stuff not coming through is clear? It was like, and look at that. You see how that's like slightly yellow? There's probably product in there. But look at that. You see how that's like not yellow at all? There's probably no product in there. And that's like the majority of the stuff that's been filtered, but it's only no yellow. So like, fuck you, fuck you. I'm just gonna work with this and filter that again, and then hopefully it works, but I fucking doubt it, but it may be, because it's the right color, but fuck you. Oh, it's not looking good at all.